So we're going to look at 4 trends that are basically explained by those 2 major trends we talked about last time. We talked about number of shells decreasing attraction. We talked about number of protons increasing attraction for those outer shells, for those outer electrons to the nucleus. If you don't understand that, you have to watch the 2 major trends video or talk to somebody who gets it. The other thing is looking at the times that you're going to break those 2 major trends, so exceptions to the rule. That was electron-electron repulsion, because if there's a repulsion because you're adding a second electron to an orbital, then the outermost electron is less attracted. Looking at transition elements, how you're adding shielding electrons as you add protons, and looking at when you fill a p instead of an s, when you fill up the s orbital or subshell and you start to fill the p subshell, the p is less stable, so it's a little less attracted. If you don't have that, then you have to watch the exceptions. Alright, so the 4 trends are these guys. Atomic radius is the first one. You can actually use it to explain the other 2. The atomic radius is all about how tightly or how close does an atom attract its electrons. More attraction, smaller radius. Also, fewer electrons to attract, smaller radius. Electronegativity, if you have a bond, how tightly will those electrons be attracted to one atom in that bond? Ionization energy is looking at basically how difficult is it to remove an electron from an atom. And electron affinity is looking at how much an atom desires an extra electron. And we'll talk about each of those if you didn't get that, because I didn't expect you to. Atomic radius, if it's more attracted, it draws in the cloud more, gets smaller. We call that greater Z effective when the outer electrons feel the positive attraction of the nucleus and get drawn in more. So this is taking into account shielding and number of protons. So smaller radius. The times you're going to have a smaller radius is when you have fewer shells, because there's less blocking. And when you have more protons, there's more to be attracted to. So the general trend for atomic radius is that as you go across, the atomic radius is going to decrease because attractions increase. And as you go down the periodic table, you're adding more shells. So there's more layers to be attracted, and there's more blocking, so there's less attraction. So it's going to increase, the atomic radius is going to increase as you go down. So let's look at which would we expect to be smaller. First we have sodium versus magnesium. So I look on the periodic table, I can see they're both on the 3rd shell. So the same amount of shielding, I can't really compare that. So then I look at the number of protons. And I can see that sodium has 11 protons attracting its electrons. Magnesium has 12 protons attracting its electrons. So with the same number of shells, so the same amount of blocking going on right here, but more protons to attract the outer electrons, this guy is going to be smaller because it draws its electrons in more. And that's what I expected, because we said, magnesium's here, sodium's here. It should be smaller because we decrease across. So sodium versus potassium, potassium's on the 4th shell, so there's going to be more shielding. I can stop there because shells are more important than the number of protons. So potassium has an extra shell to attract. It's going to have more blocking going on here, so these outer electrons that we're curious about are going to be able to have a lower Z effective or be attracted to that nucleus less. So that means sodium is smaller with its fewer shells and less shielding. Greater Z effective. Right. So electronegativity is when an atom is in a bond, and we're looking at how much that atom attracts the electrons in that bond. And the time that it's going to attract more, again, we go to shielding and protons. If there's less shielding, there's less blocking going on, so those electrons being shared are going to be drawn in more. And if there's more protons, then there's going to be more attraction. So the electronegativity is going to increase with attraction. So as we go across, there's more protons, there's more attraction. That means the electronegativity is going to increase. And as we go down, there's more shells, so there's going to be more blocking. That means it's going to decrease as we go down. All right, so if we wanted to look at which atom would attract electrons more to it, I think it's nice to have something that you just have memorized, and most of us, I think, memorized already for APChem that fluorine is the most electronegative atom, because it's up here. And And we know that electronegativity is going to increase up and increase across. There's fluorine. But we have to be able to explain what we already know, but this can anchor our answer so we don't question ourselves. So fluorine and chlorine are going to have 2 and 3 shells. So there's fluorine. Here's chlorine. Already I can see more shells means that these outer electrons are going to be blocked more from the nucleus, having a lower Z effective. Plus there's more shells, so they're just a greater radius. They're farther away. So these electrons are less attracted to the nucleus than these electrons would be in a bond. So when they're being shared in a bond, fluorine is going to attract its electrons more. If I look at oxygen versus fluorine, well, the fluorine had 9 protons. This is fluorine. Oxygen also has 2 shells, and oxygen has 8 protons in the center. So the fluorine has more protons to attract the electrons towards it. It's the maximum amount of protons you can fit in an atom with only 2 shells, with only 2 electrons shielding. So that means it's going to attract its electrons closer, has a smaller radius, it has a greater Z effective, so fluorine is smaller. And it's what we expected, because we expect, smaller. So the fluorine is going to have a greater electronegativity. And that's what we expected, because fluorine has the greatest electronegativity. Ionization energy. An ion is a charged atom, so we know we're going to do something with removing and adding electrons. It's all about the electrons. More attraction means it's going to be harder to remove the electron. And if you want the textbook definition, ionization energy is the amount of energy needed to remove a mole of electrons from a mole of gaseous atoms. Okay, so how hard it is to remove these electrons. So the equation that represents this, if you're ever asked, write the equation representing the ionization energy of fluorine. Start with a fluorine atom and show that it becomes a fluorine ion, a cation. It's positive, and that's rare. You know, fluorine typically doesn't do that, but this is ionization energy. We're removing a mole of electrons. And there's the electrons that were separated. Okay, if you had second ionization energy, you're going to start with that positive ion that you already made because you already moved 1. And then you remove a second electron to make it a 2+ charge. Okay, so ionization energy is going to be greater if there's fewer electron shells because there's less blocking. If there's the same number of shells or more protons because that's more attraction of those outer electrons to the nucleus, it's harder to remove. We also have to start looking at these exceptions. So when you have less electron-electron repulsion, you're going to have a greater ionization energy. So let's look at that one real quick. We just said ionization energy is going to increase across, and it's going to decrease down due to extra shells. Let's look at something that would have more electron-electron repulsion. So if I were to compare nitrogen, I'm just going to draw the outer orbital box diagram, the orbital box diagram for the outer electrons. It has 5 valence electrons, so 1, 2, 3, 4, 5. And oxygen has 1, 2, 3, 4, 5, 6. Following Hund's rule. Okay, so we would expect the ionization energy to be greater for the oxygen than we would for the nitrogen, because we're going across the periodic table. However, if we find out that it's not, something we can look at is, well, this guy has electron-electron repulsion. That makes it easier to remove. It's a negative magnet repelling this other electron in the same orbital. The other thing to look at is that P subshell is less stable than the S subshell. So for example, if you were looking at removing electrons from beryllium versus boron, beryllium only has 2 valence electrons. So it's like this, that's my beryllium. Boron has 3, so it's like that. We would expect that since we're going across the periodic table as we go from beryllium to boron, we would expect that it would be more difficult to remove from boron. However, you're removing from a P, so we'd want to take that into account. So if we were told that it violated that trend, that could be an explanation for it. Also, if you're looking at transition metals, you can always say that you're adding shielding electrons as you add protons, which can break the trend that we'd expect to see, that ionization energy increases across and decreases down. electron affinity. So the last one, it's how attracted is an atom to an extra electron. And the way this is measured is you start with the atom with its electron already, so it's a negative ion, an anion, and then we look at how difficult is it to go back down to just being an atom. So how difficult is it to remove that negative electron from that nucleus? You're going to have more affinity if there's fewer electron shells, because that means there's less shielding, and also it's closer, shorter radius. When there's more protons, because that's more attraction. And then these are really big in electron affinity. We break the trend all the time. So you're going to want to look at, are you adding electron-electron repulsion by adding an extra electron? So for example, if we're adding an electron to carbon, carbon has 4 valence electrons, so its orbital box diagram is 1, 2, 3, 4, versus adding an extra electron to nitrogen. Nitrogen has 5 valence electrons, so 1, 2, 3, 4, 5. If we add an extra electron to each of these, carbon places it there, nitrogen places it there. This has electron-electron repulsion. That's not favored. So even though electron affinity should increase across due to more protons, should increase across, and it should decrease down, less attraction because there's more shielding, decrease down. Okay, even though we'd expect that, we break that trend as we go from carbon to nitrogen, because nitrogen is adding electron-electron repulsion. The other big thing to look at is, are you adding electron to a higher subshell? So that would again be looking at something like the boron and beryllium thing. We'd expect electron affinity should increase across due to more protons, but if we add an electron to, let's look at lithium, and we'll look at beryllium. So we'd expect that electron, or that beryllium with more protons would attract an electron more, so it would favor to gain an electron more. But lithium has 1 valence electron, beryllium has 2. So when you add an electron to lithium, you get to put it in that more stable S subshell. When you add it to beryllium, the S subshell is full. You have to jump up and start filling the P, and that's less favored. These are also going to be inconsistent as you go across transition metals.